The screen is visible. So let me quickly refresh this and put it part in the we said about the interpolation problem in sense.
I had a doubt. So
Yeah.
right now in the assignment we had discussed the theory, but there were no numericals solved. So where can we actually get the
Which
question bank
numerical?
or something to solve this?
We'll be solving. Don't worry. For this particular chapter, right?
Yes,
And
sir. For this.
one problem I have already solved, madam. This is the problem already I have solved, right? Then how can you say that we have not solved it?
Yes, sir. But additional questions, where can we get it from?
You have the book with you, right?
Okay, the PDF that was sent
Yeah.
initially.
I have not sent any PDF. You might have got this book, the Simon Hayek Neural Networks and Learning Machine, so that you can refer to. Anyway, so once we have this, so last class we talked about this interpolation in strict sense. We wanted to see that if we are going to implement this RBFN, as somebody has also asked some doubts, how do we find the parameters and all? So don't worry, we'll come. We can complete this today. So for that, of course, we have to go through this, and we have seen this. This is what we mean by interpolation in strict sense, means through a particular function which you are trying to find it out. Each and every data point it has to go through, and if it is strictly interpolation in strict sense, means for each data point, if you substitute in that function, the desired value you should get it. So this is what it uh, mean by interpolation in strict sense. And we say that basically in RBF we have the basically it consists of choosing a function f of the form something like this, where we have weights, and we know that weights comes into picture from the hidden layer to the output layer. There is no weight between input layer to hidden layer. Remember, in case of RBFN, there is nothing, there is no such provision. Okay. So that we saw, and now instead of this, if I put something like this, which I have already done it, but I'm just doing so that continuum and that today things will start. If I say xj, so as per the condition of on interpolation in strict sense, fxj I can equate to dj, right? So this way, and this we can write it for many examples. We have considered only one, so many which we can consider. So something like this. If I take x1, x2, x3, etc. So this is of course in the equation we can put it in matrix form and something like this, and ultimately where each phi 1 1 is nothing but this particular thing, and we can represent this in as a vectorial notation, and this comes to be phi w equal to d, right? And then actually the ultimate aim is to find this weight. Now and for the weights, if you have this all these functions calculated properly, properly means accurately, all this radial basis function, then finding weight is not a problem. You will be able to do it. But there are certain caveat over there. And of course, we know that because finding this, we need to ensure that this is a non-singular, and this is what should I say? And we have to ensure that it has to be a inverse can be found. So in order to find the inverse, there is a Michaelis theorem which ensures that if those data points are distinct, then the interpolation matrix so formed using this will be non-singular. It is guaranteed. And of course, we are not going to prove this anymore. And when the dimensionality of the hidden space is less than n, we can find this, which minimizes this, where we have something like this. And where here, instead of finding a solution as per the previous one, here we have the solution which is pseudo inverse. So basically, you will not be getting a square matrix. Your interpolation won't be a square matrix. And if you remember that I talked about the pseudo inverse when I was reviewing this linear algebra. Okay. So in that case, you have to go for pseudo inverse. Now, once we have something like this, so there are certain problems also, and these are of course typical RBF, which also I describe multi-quartex, inverse multi-quartex, and Gaussian. For the most of the part of this particular module, we'll be talking about this Gaussian function as a radial basis function. And now we'll come to this. So this we have seen in a conventional as per this interpolation theory that And that's why there was a question that if the number of data points are, say, n, definitely the number of neurons required in the hidden space is also equal to n. And everybody has done almost correct. So this is the conventional way. And you know the problem it is, you can imagine the size of the hidden space if the data set is very large. So that's why that also you can get an idea that why even though RBFN is very good and it seems to be so good without complexity of the network, there is no bias concept much, there's no multi-layer kind of stuff, and it is doing the job effectively better than MLP, then why we don't go for this? So this is one of the reason you can think of that. The dimensionality of the hidden space is too large to handle if the data points, if the training data is too large. In such situation, this is not a practical way of doing it, at least the current scenario. But of course, there is a way to make it practical, and this we'll discuss about this. So this will be always something of this form. And so this is, of course, as mentioned that henceforward. Forward. Hence, fourth, we'll be discussing about this Gaussian function as a radial basis function. Now, of course, when we formulate this RBFN, Y interpolation is quite neat, straightforward, no confusion. But training sample is typically noisy. There may be some repetition of the data, redundant data will be there, some missing values will be there. Then use of interpolation based on noisy data could lead to misleading results, and obviously the size also. So we need a different approach for design of an RBFN, not strictly as per the interpolation theory. We know that it is not practical if the data size is too large. So here we can see that there's a redundancy of neurons in the hidden layer by virtue of the redundancy that may be inherent in the training sample. Not only redundancy, if the data set is too large, then the hidden spaces, you can say that is burst like anything. Then it's very difficult to handle some 10,000 neurons in a hidden space. And if you have 10,000 data points, so you can just imagine how complex it will be. So it is always a good design practice to make size of the hidden layer a fraction of the size of the training sample. When the question comes, a fraction of the size of the training sample, what do we really mean by that? Okay. And how do I get to know about this? So for that, so function approximation realize both RBFN structure has the same mathematical form. Earlier we used to say n, now I am calling as some particular k, and that one will have something on this idea about the k things. We'll see what is going to happen. So this is the structure of a practical RBF network. So what is this? And somebody has also pointed out that how do I find the centers? How do I find the center? So remember this, center is not a problem because we're finding center at a particular data point, and then we, in this particular case, either it is interpolation wise or the practical. But in practical scenario, if the number of neurons you decide that in the hidden space is k, then the center will be chosen accordingly. Okay, and this I'll be talking about. And definitely this k is always much lesser than as compared to n, but of course it is definitely lesser than n. That is the total number of data points in the training data set. Now the question comes, how do I choose k? Any guess? How do I choose k? If you have some sort of idea, means it's possible that can we do some sort of if the data point is there, I want to know that is there any groupings over there, whether some data points belongs to some one particular group, and if that may be possibility, can I go for that kind of that many neurons as far as hidden space is concerned. So how do you do that? How do you do that? If the data point is there and you want to find some sort of groups, how many groups are there in the given data points, how will come to know about it? Is there any tool for that? Anybody?
Similarity coefficient.
Similarity. Okay. But similarity, how does it help me to find a number of groups? I'm saying number of groups. Of course, similarity measure is required. Based on that only we'll be able to find. But I want to find a number of groups.
So
Do you
like
use
by
it?
plotting, we can
What? What?
by plotting and k-means we can find like
Yes, yes, yes,
clusters.
yes. So you are very near to that answer. Effectively, that is the exact one. So if you have, so there are many clustering algorithms, and K-means is the simplest, and the reason is because it's a very is computational complexity is linear, and it is simple to implement also. And okay, and you are very familiar, so we'll be doing that only. So we'll go for k-means clustering, and that effectively it will give you some idea how many k's will be there. So I'll just take you through some of the theoretical background on peanuts. This one, tnuts regarding not peanuts, sorry, tnuts about this clustering, and some sort of formalism will be associated with that. We'll look into it so that we can formalize that how do I reframe this clustering part, so as far as RBFN is concerned, so that it becomes recursive in nature. K-means clustering is will be doing it. So the key issue while designing a practical RBFN to find a parameter of Gaussian function is basically using unlabeled data. We'll see how do we go about. If unlabeled data means we don't have about the desired value, let's say, is only the data is given to us. How do I go for this? And such kind of scenario is nothing but we normally go for some sort of a clustering approach. The solution is deeply rooted in clustering if you want to find them, the kind of groups, etc. And we know that it's a conventional definition of clustering is that it's basically it's a form of unsupervised learning whereby a set of observation, when I say observation means some data points, is partitioned into a natural groupings or clusters of patterns in such a way that the measure of similarity between any pair of observation assigned to each cluster minimizes a specified cost function. Some sort of cost function is tried to minimize. Okay. And here it says that a measure of similarity between any pair of observations. So some sort of measure of similarity is required. And you know that in case of k-means, what kind of measure of similarity you use? Which similarity measure you use? There are so many. Which one you use? Hello? Hello? Sorry, I was not able to hear. Anybody?
Euclidean norm? Or
Yes. Basically, we use square Euclidean norm or Euclidean norm for as a similarity measure. Yes. So we'll choose k-means clustering due to its performance and ease of implementation. There are many clustering effectively more efficient than k-means, but k-means is of course is very easy to implement and its complexity is linear. So for this, let's say that these many data points or n data points are there, and X may be, of course, a set of multidimensional observation. When I say set of multidimensional observation, I can say that each and every data point is a m dimension or whatever L dimension, and that is to be partitioned into a proposed set of K clusters. So K somehow you define or you get some idea based on the plot the what could be the value of K, and of course this K will be less than the total number of data points. And then we have a some sort of encoder function. So let's say j equal to c of I, where I is varying from 1 to n, and basically it denotes nothing but many to one mapper. Ultimately what it does, it behaves like an encoder, means any data point is there, and suppose we don't know what is the structure of this C at this moment. And what it does, based on certain property, if your particular data point satisfies, is maps to a particular cluster called J. So that's what is mentioned, which assign the ith data point xi to the jth cluster according to the rule yet to be defined. Let's say we don't know what is the rule, and you can guess what could be the rule. So for encoding, we need a measure of similarity between two vectors. Let's say xi and xi prime, which are denoting by xi and xi prime, which are denoting by d, right? And we know that when d is small enough, we assign xi and xi to the same cluster. Otherwise, they are assigned to different clusters. So this is normally what you do. Now we'll see soon what is this d, so which you already seen that. So now suppose this, so we use the following cost function to optimize the clustering process. And of course, j of c based on this encoding function. 1 by 2 I equal to 1 to k, some k number of clusters may be there. And then we have this, let's say the ith component is there if meeting certain requirement maps to j cluster, and ith I prime if maps to this one with j cluster. Based on means the small value is there or not. So dxi xi prime. We have to see what is this nature of d. So again, I have written this here for sake of reproduction, or you can say that for ease, or what they say, reference. So when we have this, so we know that basically for any prescribed value of k, we need to find the encoder. Basically, we need to find the encoder ci equal to j, or the cost function j is to be minimized, right? So I need to find this value of c, and before that, so far encoder c is unknown. We don't know what is that. Means what kind of measure we are using to say that something is lesser or more. So which we can define it. So basically in conventional k-means, what happens at clustering, we use basically a squared Euclidean norm to as a similarity measure. So once we have this cost function equation will be updated again, and it becomes something like this. This is straightforward. So remember that here two things are there. We are comparing them. That's why there's two summation signs and one here to find the number of clusters over there. So this is the way why it is written like this. Now in this, there are some observations we made. So we again, here I have rewritten just for the reference. So we observe following points. We know that squared Euclidean distance measure is basically symmetric. So it doesn't matter whether I write xi minus xi prime and take the Euclidean norm square, or xi prime minus xi take the Euclidean norm square. So it is symmetric. And second is the inner summation here. This part is read as follows. So we have few interpretation about it. So for a given xi prime, this one, the encoder C assigns to cluster J all observations xi prime that are closest to xi in some statistical sense, of course. Means closure, when I say this, closest to xi. So except for a scaling factor, suppose if I include a scaling factor here, so it is nothing but it is just indicating the estimate of the mean vector pertaining to cluster J, is finding the mean only. That's all. And that particular scaling factor could be 1 by j. So if you forget this point completely, and if I write here 1 by j, so this entire part is nothing but as if you are estimating the mean vector. Okay. Where of course ng is nothing but the number of data points within cluster J. Whatever you have cluster, there is a number of data points if I find it. So this indicates as if it is a estimate of mean vector, and that's why soon we'll come to know why we call it as a k-means clustering. So then you come to know that these are so many things, and k number of means are there. We are going to add it. From that it derives names k-means clustering. Anyway, so considering these data points, that is symmetric and it is a mean factor associated with that. So instead of that, we just write mean of that one, and it is square of it. So when I say for mean for this one, due to this particular mean component, one summation get absorbed over there. So we don't write it anymore. So we just write like this. So function, basically cost function, gets updated to something like this, right? So here this particular mu j denotes basically estimated mean vector associated with the cluster J. Associated mean vector. Remember, it's not one, it's a vector. So we rewrite like this here, and in the light of modified cost function, we restate the clustering problem as follows. Now that because our cost function has been updated, so we have to update our definition of clustering in following ways. So we say that given a set of n observation, find the encoder C that assigns this observation to k clusters in such a way that within each cluster, the average measure of dissimilarity of the assigned observation from the cluster mean is minimized. Here, please note that the name here, not similarity, dissimilarity. Means because in each and every cluster, only those data points should be included which are similar. If something is lesser, it is dissimilar, so we have to ensure that that is minimized. We can say that. Or you put it in different word, you have to ensure that we are putting only those data points, or the clustering is done in such a way that misclustering has been minimized. Means something belongs to cluster A. If it is in B, so that number should be minimized. So what we do, how do we find a C so that it get minimized? Now in that case, what we do here also something has to be seen because it is square, and if you remember this minus this is like a mean square, and this entire part is, so we can interpret this entire cost function for scaling factor. If I include a scaling factor again, it will come. The inner summation in this equation is an estimate of the variance of the observation associated with cluster G for a given encoder C. It is nothing but variance, because if you remember this Gaussian formula, exp minus, you see 1 by 2 sigma square and x minus square. So basically you something like variance is given. So basically it's nothing but it's a variance only. This entire part is variance. So we may view the cost function JC as a measure of total cluster variance. If you see here, if I add this entire part, this one, and so the summation also goes, so I can write j equal to 1 to k sigma j square. You are doing nothing but finding the measure of total cluster variance resulting from the assignment of all n observation to k clusters that are made by C. That is the encoder function. And of course, with encoder C being unknown, how do we minimize the cost function? Because C I don't know, let's say. How do we minimize this cost function? So to address this question, we use an iterative descent algorithm, and each iteration of which involves a two-step optimization process, and we'll see that. So first what we do that, it uses nearest neighbor rule to minimize the cost function with respect to this mean for a given encoder. And I hope you all know what you mean by NNR rule, that is nearest neighbor rule. Second step minimizes the second step is that for this iterative descent rule is that minimizes the inner summation with respect to encoder C for a given mean vector mu j. Because remember that mu is not only one, it's a vector. It's basically array of values. So we'll see that. So this two iterative procedure is continue until convergence is achieved. When I say convergence here, what do you mean by convergence here? How do you know that convergence has happened? Any idea? How do you know convergence has happened? Okay, forget about this. In a conventional k-mean clustering, when you do, which you might have studied in data mining or all, how do you know that convergence has happened? Anybody? बोलो भाई, कसम खा ली है क्या? बोलना ही नहीं है. Okay. So basically you are finding this when you initially you start with the centroid in k-means clustering also centroid, and those values are quite random. Sometime you have some way to have a informed initialization, but otherwise you can start from random. And you see that this every now and then, after each and every iteration, this centroid keeps on changing. So when you feel that after multiple iteration, of course, because k-means also conventional k-means also the two-step process. So when you do it, what happens that after certain iteration, when convergence happened, the value of centroid does not change anymore, or you can say that it changes after few decimal places only, which is insignificant. So this is how you come to know that convergence has happened. Now mathematically we can put it this in this particular term. The k-means algorithm proceeds in two steps. These are just mathematical terms I'm going to put it across. For a given encoder C, the total cluster variance is minimized with respect to the assigned set of cluster means. Because basically you initially start, okay, there are 10 clusters, and initially 10 centroids you take it. So that is those centroids are nothing but the mean, cluster means only. And you minimize this total variance with respect to these clusters only, right? So there is two process. One way that in once you hold the centroid or the mean fixed, and based on that you minimize the total variance. In the second step, what happens? Whatever the calculation you do here, and based on that you update the value of cluster. So that is, we perform the following minimization process, what I've said here, that with this, we optimize this particular value function, which is nothing but the total cluster variance for a given C. Okay. Now, having compute the optimized cluster means you have done in step 1. We optimize the encoder C as something like this. For that value of j within 1 and k, of course, we find that value of j which is going to minimize this, and this is obvious. Suppose this is your data point and you want to know whether it belongs to that particular cluster or not, which particular cluster is more suitable. You will choose that one with which it is having the minimum value of this Euclidean norm square. So this is how the two-step process normally happens for this. Now, starting from some initial choice of the encoder, algorithm goes back and forth between these two steps until there is no further change in the cluster assignments. And this is the convention it happens. Now, you know that the convergence of this algorithm is assured, but it lacks global optimality criteria. Means there is no way that we can show that k-means is always leads to a global optima. Or global optima, what I mean to say, these are the most optimal clusters or the centroids, because it's keep back and forth. But it is very quick and dirty idea. Or when I say dirty, it doesn't mean dirty. What I mean to say, there's nothing to try now, and you want to go for some clustering, so quickly go for k-means and you get some idea how it is happened. But something, if you want this clustering to be happens very accurately, then later refinement you can do. But initially it gives a very fantastic, beautiful idea about the algorithm is having what kind of cluster structure. So of course this algorithm has this advantages. You can say that k-means is computationally efficient, its complexity is linear in the number of clusters, and when the clusters are compactly distributed in data space, they are faithfully decoded by the algorithms without any problem. And here, of course, to initialize the k-means algorithm, normally what we do, we start the algorithm with many different random choices for the mean. That's what I said. For the proposed size k, and this k based on the plot, you may get some idea, and choose the particular set for which the double summation is cost function, assume the smallest value. This is what you do. Now the problem is there. Okay, so far we know this is good. We have found this k-means and all those things. Now, can you give me an idea, man, how this k-means fits into Covers theorem framework? Why this guy is talking about k-means clustering, something which I've studied in data mining, what it has to do with the neural network? And if it is also, we are talking about the Covers theorem, and we say as per this Covers theorem, it says that a complex nonlinear distributed data, if mapped in nonlinear in higher dimension, or simply to say that, it says that complex classification problem, pattern classification problem mapped into higher dimension becomes linearly separable. That is Covers theorem, simple, right? And that's what on that day I gave it, try to explain on the board, means what do I mean by higher dimension? How if I'm adding one dimension, it helps me to see that, oh, it's a linearly separable. Now in that context, in this particular big picture, can you give me some idea whether K-means fit into Covers theorem framework? Does it fit or not? Anybody? Okay, let's try to enumerate one by one. What do you mean by Covers theorem? So first of all, we need a no linear transformation. Is there any no linear transformation happening in K-means clustering? Hello?
Yes, sir.
Whether any no linear transformation happening in K-means clustering? Anywhere?
No.
Okay. The function which you use is Euclidean norm square. What kind of function it is? Is it a linear function?
Uh, no. So it is happening.
Yeah, it is happening. So first thing that we can see that our Euclidean norm square itself is a nonlinear transformation, and this is the first point, that is no linear mapping. Second is that each and every cluster discovered by K-means algorithm is nothing like but a computational unit in the hidden space of RBFN. You can say in that way, it's like a hidden layer. So basically, also the number of cluster is large. K means algorithm will satisfy other requirements of Cover's theorem also. So this is how we can say that yes, K-means clustering fits into the even the Covers theorem framework. So you may be asked something like that, state that how the K-means cluster fits into the Covers theorem framework. So you should be in a position to argue and accordingly state the reason why is it so. Okay. Now so far so good. We now know that okay, K-means clustering happening, things are happening. Okay, well, but there is some problem with this, and that's why we need to go something called recursive least square estimation of weight vector. Remember that here we discuss about this so far. What we have discussed is, let me go to the diagram once again. Here there is no weight. Now using all this k-mean etc and all these things, finally we are saying that okay, I can identify those many clusters, and those clusters centers can be, that is a mu etc, you can find it across. So that will be my center now. So center I found. So somebody asked the question, what is my center, right? Hello, somebody asked this question, how do I find the center of my this one, what should I say, Gaussian parameters. So effectively the one of the parameter of the Gaussian radial basis function network is nothing but the center. So what will be the center now? How do you know it? Any idea? Have you got it so far? And I told that
You
this will cover.
the centroid of the
Yes, yes. So whatever the data is there, you apply the k-means algorithm, and based on this algorithm, once you identify how many this one is there, clusters are there, and once it converges, so the centroids of those particular clusters that become the centroid for the respective hidden layer neuron. Okay, so this part we have found. Now the question is, how do I find this W man that is still left? That is the weight space, and we told that once we map input vector to the hidden space, from the hidden space to map to this one, it is basically linear. When I say linear, so we have to find some technique, either least square approach, which is very simple to go for. That is a linear filtering problem is there. Remember that this least square etc. I talked about physically filtering problem, and we say that that is the LMS algorithm and all. So we talk about some, and we said that it's so beautiful RBF structure is that any nonlinear filtering problem can be mapped to linear filtering problem just by mapping into the higher dimension space. By the same analogy, we can do this, but now the question is how do I get this? For that, we'll try to apply the same least square algorithm, but customized to this scenario because the number of data points are too high and the dimension of the required matrix is humongous. So we cannot solve this problem in a conventional way. Rather, we have to go for some sort of recursive function. So that we'll see now. I hope now you are able to fit into this bigger picture of Covers theorem, what a role is being played by k-means cluster, or let's say for any clustering technique, not necessarily k-means. So, so that is clear, I hope. Now we'll go for this one. This I've talked about. Yes, recursive least square estimation of weight. Why least square? As I told, basically that particular part from hidden space to the output space is linear, and we have to find this weight, estimate the weight in some sort of statistical sense. In some statistical sense, we are going to the very rudimentary way of going is nothing but least square estimation of that. Means difference and square and find the least of it. Okay. So K-means algorithm perform computation in a recursive manner. You saw that a recursive manner happens. It's not straightforward. So we'll recast the method of least square for computing weight vector in the output layer of RBFN in a recursive manner also. So that's what we'll do. And how do we recast that? We have to see that. So some part I could not somehow complete this slides for this. So some part I'll complete the slide and somehow I'll use the board because I was busy with something else. So let's see this. So normal equation for this least square estimation is normally given by this Rn, and remember this W cap. Whenever in machine learning or statistical learning, whenever it comes to cap, means something this you want to estimate. It's an estimated value, right? N equal to Rn. So we'll try to understand what is R, what is W, what is small r. So all these things are there. So basically three components are there. This capital R, if there are k number of clusters, so this will give you basically nothing but the k by k cross k correlation. So we'll see this three terms. So first, this R is nothing but k cross k correlation function of hidden units. Here the unit output means from the hidden space, which is defined by Rn. We are using this symbol. Sorry, there is a typo from my side. It should not be I equal to n, rather it should be I equal to 1 and n, some n, and basically we are all using a discrete function of n time as a n. That's why this n. And this phi xi and phi t xi, this phi is nothing but it is your radial basis function, okay? And this xi is a data point, and remember that it's basically when we go for correlation finding, correlation, it is always a this one outer product, not an inner product. That's why phi t, and then sum of all those terms, okay? Where of course it is also explained what is phi means. So phi xi is not 1 because it depends, because you are the dimensionality of the hidden space is k, dimensionality of the hidden space is k. So each phi will be mapped to this one. You remember that I discussed on that day what do I mean by mapping to the higher dimension, right? If I have this many functions, k number of functions, even though k is higher as compared to the dimensionality of xi, I'll be mapped to those things, and this is how you'll be getting. So each phi is nothing but those many k vector or k data points. You can see that, okay? So once you have this, and of course, each phi is finally we define, it basically is a radial basis function, on particularly is a Gaussian a radial function. So the Gaussian function basically, and radial we know that due to this particular nature, due to Euclidean sense, it make use of it. So this phi is denoted to you. Now next comes this R. What is R? Do you have any idea what could be this R? Any guess? Any guess? So this R is small r is nothing, but it is basically a, cross correlation between the desired response at the output, desired response of the output, and the output of the RBF network and the hidden units between that. So that is the cross correlation. So which we denoted by this. So Rn equal to sorry, summation I equal to 1 phi xi. So output of this phi xi is nothing but the output of the hidden space, and this is the desired output. So you find a cross correlation between the two. So this is Rn, and W is this W is basically unknown weight vector, which is optimized in the least square sense. So we know what do you mean by least square sense. Now the question comes in this, if that is a problem, so far earlier we used to do very simple thing. Okay man, this Rn anyway is a matrix, I can find it very easily. And what's a big deal? I can always find the estimation of W equal to R inverse and small rn, done. So what's the problem? This is straightforward. Can you see any problem here? Are you getting some the point which I'm trying to put forth here? See, if everything is clear with us, okay, R is given, this capital R is given, and this is the normal equation for the least square, and objective is to find this W. What's the problem? I can say this R here, R inverse multiplied with Rm, done. Then what's the big fuss about it? Why you are so much focusing about here? What could be the problem? Hmm? What could be the problem? Any guess? See, the major problem will happen something like this. If k is small, the number is small, then this matrix are very easy to handle. But imagine the case that the value of k is very large, the dimensionality of the hidden space is very large. So you can imagine the dimensionality of this matrix. Suppose if I have, say, 10,000 data points are there, and let's say out of 10,000 data points, you found that the dimension of the hidden space should be 100. Even for the 100, basically you can imagine it's a 100 cross 100 matrix, man, and finding the inverse is not a simple thing. And even just example I'm giving, and this 100 may go scale up further. So in that case, a conventional way of this one finding the inverse of this particular matrix will be quite demanding. So we'll go for nothing but some sort of recursive approach which will help me to do this job easily. Okay, so that we'll see now. Whether this is clear, why we are going for recursive least square estimation instead of conventional go for way of estimation. Is it clear? Hello? Hello? Okay. Fine. So we'll look into this. So I could have written this directly. So let's say that we'll start with this. R we know. So we'll reformulate the cross correlation vector. So cross correlation vector, if you see from this particular slide, it is this, right? This. So this I'm reformulating. I equal to 1 to n phi x at di. I'm just trying to put it across. So what I'm doing is that here. So do you mind if I, instead of writing like this, if I write like this? So I equal to 1 to, instead of going to n number of data points, I'll go to only n minus 1 data points. And the last data point I'll write phi x and dn. Okay. Can I do so? Yes or no? Can I do so? Or I should say, may I do so? Okay. So we can do this. If you don't say anything, I have to say this. So we can do this. And so this point, if this is Rn for this equation, definitely for this we can write Rn minus 1 as far as this is concerned. This will continue to be there. And now this one, this Rn minus 1, if it was, if Rn equal to Rn W cap n, do you mind if I write Rn minus 1 equal to capital Rn minus 1 W cap n minus 1? I can do so, yes. And I have done the same way. Nothing great in that. Just I have replaced this cross correlation with the its value, and this continue to be there. Now this continue to be there. So something you have to do with this, right? So I add and subtract this particular term phi n phi t n w n minus 1 from to the above equation. When I add and subtract, now the question is, how do I know that I have to add or subtract? So adding and subtracting is required only because I want to transform this equation in some particular format. Then only. Otherwise, there is no reason why should I do this, right? So when I add and subtract this, let's say I'm adding this entire part here. If I'm adding this entire part here and taking w cap n minus 1 common, so I have this part. Because I have added here, I have to subtract it also. When I subtract this part from this one, and phi n I can take common. If I take phi n common and this is there, then I can say this. This is the positive part. So dn minus phi tn wn minus 1. So same thing I can write in this particular form. And once I have this, so there is something to be noted. What is happening? Now this, I'll write this particular thing in bold because this completes my this slide only because it's incomplete. So I'll take it to the board. Take it to the board. So for that, let me write on the board. So we have this so far with us. Mm, Let me write this completely. Just a minute. So we have cross correlation Rn equal to Rn minus 1 plus phi n and phi t n, and this is Wn minus 1, right? Plus phi n and Dn minus phi t n and this. Okay, we got this. Now from this part, if you see this one, this particular part, this is nothing, I can write it as Rn. Why I can do so? Because this is for till n minus 1, this is the correlation matrix. For the nth point, this is also the correlation matrix. So n minus 1 point plus nth point, if I do, this but equal to Rn straight away. So I can write it that Rn, this one is nothing but, I can always write n minus 1 plus phi n phi t n, right? This is the case. Now for this part, whatever is there in the bracket here, so let me write in some form, and let me just write something alpha n. Let's see this, what this alpha n means and what does it mean. So I'm just writing it across here. So dn minus phi t n w n minus 1, of course. So this is w n minus 1, this entire part is there. So if I can do this something like this, dn minus, first of all, can I do so here? I just did this ATB, I can write BTA because if this there. And why did I do so? This is some particular objective you want to meet, and what is that particular objective, that we'll see here. This alpha n is called a prior estimation error because it's error. Why? Because you see that this is the desired value and this is maybe the predicted value based on the whatever the estimation you had, estimation for W, right? Based on that, so this kind of error you have. So this alpha is also called prior estimation error. Prior estimation error. Okay. Uh, so this is there. Now let's see this. Now, including this, can I update this equation? So how do I? When I update this equation, so this becomes Rn equal to Rn Wn minus 1 plus phi n and this alpha n, where alpha is a prior estimation error. Now, accordingly, so this is, remember, this is Rn, this is Rn, but because we know that Rn equal to is nothing but Rn Wn. We have known, we started with this as far as least square estimation is concerned. So comparing these two equations, so I can, instead of this, I can write R of n and Wn equal to Rn Wn minus 1 plus phi of n alpha n. Once you have this, and we can of course choose to find this, and we can update this in the particular part. And how do I do this? we want this updated value, this we want for this. So R, I can take it there. So just hold on. You may say that, man, what a big deal. This you could have done earlier also. Plus R inverse N, phi of N, alpha N. So this is the equation for finding the title we talk about this. That is the recursive least square algorithm. That will give the basically this. Now the question remain there same, which I said that is very straightforward, that Rn equal to Wn is there, and if this Rn is there, I could have just found like this. This I could have done this. Then why all these things? So then I raised the question that in that case dimensionality of this Rn is very high. Then this simple finding of inverse may not be possible. And we did this process to show that. But this is we have not completed. We are just showing that how do I find this weight when I go for the recursive way of finding. Now the questions come, how do I find this one when the dimensionality is very large? So this is the question which is unanswered, and that we'll discuss now. Okay. Now, so we are going for the recursive formula. So see that this recursive form, this is nothing but a recursive formula for least square method. How do I find the weights? So that we have done. But within this R inverse computation is still left out. We said that we have not yet found a solution. We have just used it. So I have to find the way to solve it. So for this, there is something we have to talk about this using the from the perspective of the matrix, and we'll see this. So we have a formula for we are looking for a formula for recursively updating this R inverse, or basically correlation matrix. So we'll consider this one. So what we are doing now, we are trying to find the recursive formula for computing. Okay, done. Now how do I do this? So for this, let's consider a matrix. First, we'll try to consider a matrix, then we put all those things in block. P inverse plus CD CT. So where it is assumed that P is non-singular, it means this exists, and A and B are of similar dimension. A and B has similar dimension. Okay. And D is another non-singular matrix with different dimension. D is another non-singular matrix with different dimension. And C is of course rectangular matrix of the appropriate dimension, we can say. Now there is something called matrix inversion lemma. So this you can find in part of this matrix calculus. So there's something called matrix inversion lemma. It's a straightforward formula you can think of. Inverse. Suppose what I'm trying to say, if this is the matrix in this particular form where this is non-singular and D is also non-singular, A and B has the same dimension, D is having different dimension, but it is non-singular, and C is basically rectangular. If that is the case, so as per matrix inversion lemma, A inverse can be computed as A equal to B minus BC D plus CT BC inverse. Don't worry, if something a question comes, this kind of formulas will be given in the hints of the paper. So if you have some that kind of thing here, you have something like this, then you can find something here straight away. Now the question comes, how do I correlate this with this? Can I have something of this one? If I do this, what is my A? What is my B? Can I have something from here, etc.? Can I go for something like this? So we'll see that. So in this, when I when you write like this, if you just remember this Rn minus 1 plus phi of n and phi t of n, which we saw earlier. When I apply for this, and then you compare with this. Compare it with this. A equal to B inverse plus, what was that? C D C T, and compare this and this, what you are going to get it. So A is equal to R of n, B inverse is equal to R n minus 1, C. When you compare here and here, can you tell me what is C and what is D? What is C and what is D? So C is nothing but phi of n, because phi of n and phi t. Obviously, D is, you can write I or 1, right? So now once you have this A, B inverse, C and D, once you substitute these values here, everything here, then you got the relation for finding the recursive relation for finding the inverse of this one. That is A inverse equal to B. B means, so you have this R inverse n minus 1 minus, I'm writing directly now, R inverse n minus 1 phi of n, phi of t n, this R inverse t n minus 1, and here 1 plus phi of t n R inverse n minus 1, and of course this phi of n. This is in substituting all these things in this. Nothing great I'm doing. I'm just substituting everything over that. Okay, because this inverse is there, this part, so this is nothing but this entire part, D. So instead of D, here you can say I. 1 is written, right? You can write I, which is written by 1. Now once you have this, so we have, remember this in the denominator, this one in the right hand side of this one, this particular equation, we have used the symmetry property. Symmetry property of what? We have used that RT n minus 1 equal to Rn minus 1. Why is it so? Can anybody tell me why is it so? Remember that whenever there is a correlation matrix, if you take the transpose of that, it is remains same. So that particular concept had been used. Now this is written little looks bit ugly and so many things are there. So effectively, see, I'm trying to put a bin now. Let me complete this, then I try to combine everything. So let me write it in more simpler fashion. So this, as far as formulation is concerned, we can, instead of inverse are appearing everywhere here, instead of that, let me just write it, okay, man, I can just say R inverse n, I'm just assuming to be P of n, safe way. So this entire particular formula, this one, wherever R inverse things are there, we can change it. So instead of inverse in everywhere, we can say P of n equal to P of n minus 1 minus P n minus 1 phi n phi Tn, and here of course again Pn minus 1, and in denominator we have, of course, we can just write it in this way: Pn minus 1 phi n phi Tn Pt n minus 1. Okay, so once we have, if you see this one, this particular thing, and you know that this is a matrix, this is a matrix, this basically it is nothing but a quadratic form. Whenever there is a quadratic form, there is a scalar thing is bound to happen. So quadratic form only. And now to provide this interpretation, we can say that. So I won't go further in this. So we'll see that. Now the question is, I have this data points. Now let me combine all these things. I have these data points, sum to n. And let's say it's a complex pattern classification problem. I need a RBFN to transform it into the higher dimension space and then linearly separate it. For that to happen, let's say I have this particular point and whatever the dimension may be, and somehow by plotting it, I came to know some k number of clusters. And k number of clusters are there, so those cluster centroids becomes the center of my those k number of neurons in the hidden space. Okay, so that we have done using your you can say that whatever the k means clustering or whatever. Now at this point you wanted to know that what is this particular data point, what is this k, what is this w, what is this w, and for this particular w to happen, for this w we want to find, and this is linear in nature, so we already have this dimensionality. We already found this 5 values, and when I have this w, so we have used this least square approach, using which we found that this is the weights which we are going to found, that which is recursive in nature. Because why is it so? Because the k-means clustering we saw is also recursive, so we have to find the weight updation equation in terms of the least square sense, and which is something like this. Once we have this, we found that the major problem is finding the correlation inverse, and this could be straightforward if the dimensionality of the correlation matrix is small. But if the dimensionality is very large, if n is very large, I cannot go for this inverse finding in conventional sense. In that case, I need to find a way so that I can have a inverse that is also recursive in nature. Here if you see, this is also recursive in nature. Once you found this, you substitute that, effectively we end up the solution here only. So we know that, right? Now I'll go back to the slide, and last somebody said this, how do we solve this some problems? So just to give you a snapshot that if you apply this, but of course here we are not applying any clustering as such, so we see that, but problem remain same. So this either you can implement either PyTorch, Python, whichever you are comfortable with. So we are visiting XOR problem, and if you remember that I started this particular chapter with the XOR story, and I show that okay man, it's so easy as compared to MLP, how can I do this? And that was that. Now having understood all these things about this RBFN, can I apply this concept for a simple problem, no linear classification problem called XOR? Answer is very much yes. So let's me have a two radial basis function phi1 and phi2 with weights w and w, and of course some bias may be there. So this we are investigating because it's basically Gaussian in nature. So this is T1 equal to 1, 1 and 0, 0. Now I invite you that what happens if the centroid is not 1, 1, it is 1, 0 and 0, 1, C. And you'll be surprised to know that, or see when you plot it, you are still able to do this. But let me go in a conventional approach. I'm not going to make a crude plot and do it, which I have done in the starting. Rather, I'll follow this particular process of this input-output relationships basically. And we have used here W because instead of writing I could have mentioned this, but here we have say equally weight whatever it may be. And due to this bias, this is added over there. So when I go for this and to fit the training data of table one here not mentioned explicitly, means all those 0, 0, 1, 0, etc. for combination of this XOR gate inputs. Once we have this, we require that basically yxt equal to dj. This is nothing but effectively is a typical interpolation problem in strict sense. That's something of that sort. So we are writing all these things. And when you do this, so of course matrix form we follow here. So this I'm following a conventional six sense. And this 111 is appearing due to this bias factor. And this entire weight space will be when you map it, nothing but WWD. And when you calculate all these things, you are getting something like this. Now here you have this basically all this calculation. This is our interpolation matrix. So this I am doing in a conventional interpolation way because the size of the data space is very small. So I could do it without any problem. Now the problem here is overdetermined in the sense that we have more data points than the free parameters. So effectively the free parameters are effectively 3 rather, and number of equations are 4. So that's why it's overdetermined. If you overdetermined things are there, definitely you cannot go for a convention. It's not a square matrix anymore. So if you see here, it's not a square matrix. Basically, it's basically 4 cross 3. It's basically a tall matrix rather than the square matrix. So we have this pseudo inverse concept, and using this, we know that phi t you'll be able to get it. Phi is already there. Multiply inverse phi t, etc. D is there with you. And once you have this, so this is the phi plus means the pseudo inverse of that. So I'm not expecting that you'll be calculating here. If the value is small, of course you can do it. This is 2 cross 2 or 3 cross 3 is there. For large value, we have to depend on some sort of computing software. And finally, when substituting all these things, we get these values of weights. So what I'm trying to, and this completes the specification of RBFN. So once we substitute these values here in this particular network, it solves this XOR problem. So this is so this is how I'm concluding this. So when I'm solving this, you will say, wow, what a big deal, man. Such a small thing you did it. So let's see. Initially, we started just to get motivated enough for RBF and that how does it solve the XOR problem and why it's very simple. And then I made a crude plot based on just by mapping and say that it solves, man, fine. But we have done all this interpolation theory developed over there. And in this particular example, I've shown that if interpolation theory you can apply in a very conventional sense, if the data space is or the data training data is very small, you can blindly go for this interpolation theory concept in a strict sense and solve using this pseudo inverse concept without any problem. However, if the data is very large, that also I've seen how do I go for a practical approach for solving or designing RBF. And in that case, whatever the data is there, you have to apply the K-means clustering, find the clusters. After all this clustering, find the centroids. Those centroids will be nothing but the centers of those hidden space networks, neurons, and then you map it. Later, you apply this recursive least square approach, which you have done to find this R also in a recursive way, and you'll be finding the synaptic, not synaptic, sorry, you'll be finding the weights for the output layer. So this is how you do. Now let me just quickly correlate that how this is compared with MLP. So basically RBFN, you know that is a single layer structure where MLP can have more than one. This is one common difference measure. And also the computational nodes of MLP located in hidden layer or in the output layer share a common neuron model. So means all the neuron if is McLeod-Spitz, everywhere is McLeod-Spitz only. Whereas in case of neurons used in RBFN, you see that hidden layer we are using a different kind of neurons, the kind of non-linear transformation they use, particularly this Gaussian function, whereas the output they use a different neural model completely. Also, the argument of the activation function of each hidden neuron in RBFN computes the Euclidean norm that you have seen that because the radial basis function basic idea depends on the Euclidean norm only. That's why they are called radial basis function, radial function. So we find the Euclidean norm between the input vector and the center of the unit. Whereas the activation function of each hidden unit in a MLP computes the inner product of the input vector and synaptic weight of that unit. This is how it does. Or MLP constructs a global approximation to nonlinear input-output mapping. RBFN uses exponentially decaying localized nonlinearity. Means if you've seen that Gaussian or any other also radial function use, so they have this particular property, exponentially decaying localized nonlinearity. When I say localized, so remember that we were talking about this multi-quadrics, inverse, and Gaussian. So those three functions, one is called localized, another is called non-localized. Localized means if you increase the value of n, sorry, phi of r tends to 0 if I increase the value r to infinite. So this is what I mean to say is localized. And this is a local approximation to nonlinear. So here it is a global approximation, there is a local approximation. Okay, so this concludes the RBFN with MLP. If you have any question tomorrow, I'll be available between 2 to 3 online, or you can come to my chamber also. I'm not going to be there in 315. Last week I went, nobody was there. So this is how. So I'll conclude here. And so, yeah.
So in the start we mentioned that RBFN relies